Well, did you see the report I faxed you, Frank? I know we're still in the red. It's been 3 weeks now. Well, you know we're going to go out of business if we don't do something about this pricing. All right, well, I'll ask Kanwal. Maybe he can help us. All right, take care. Bye-bye. Enough with the bad news, Euclid. Kill spreadsheet. Oh, hi, Kanwal.
Oh, hi, Christine. How are things going today?
Not bad. I just don't think I'm cut out to be a business tycoon, though. I just can't seem to turn a profit.
You know, I told you yesterday your pricing is too high.
I agree, but Frank...
Yeah, your cousin?
Yes, and business partner. He's not convinced that lowering the price will recover the costs. Never mind turn a profit.
You know, I think I can help convince him. Give me the latest information.
Okay. A couple of weeks ago, we ran an ad in the Math News Weekly selling these beautiful Math Shop fridge magnets for the low, low price of $24.
$24, don't you think that's a little steep for fridge magnets?
Obviously, okay?
Okay, sorry. Did you get any sales?
Nothing. Nada. Zero. Not a single reply. So then I thought, well, maybe the price was too high. So I convinced Frank to run the same ad again the next week, only lower the price by $1 to $23.
Okay, did you get any customers?
Yes, I got 10 orders. So then the next week again, I convinced him to lower another $1 to $22.
Okay.
And then I got, now wait for it, 20 orders.
Well, the pattern's pretty clear.
Of course. The lower the price, the more revenue I get. But still, there's something I need to know. I'm preparing the next ad today. But before I can finish it, I need to know just how far I can drop the price.
Well, based on this pattern, you will get the most sales if you reduced your price to 0.
Right. And if I give away money with each set of magnets, I could sell a whole bunch. Come on, Kanwal, let's get serious. I gotta turn a profit here.
Okay, I think this problem can be solved by plotting a quadratic function. And since that's our topic for today, let's start the show.
Yes, you're watching Math Shop, the program where we minimize the pain and maximize the gain as we make math part of your everyday life. I'm Christine, and this is my Math Shop partner and world-class math coach, Kanwal.
Hello.
And this high-tech piece of furniture over here is my homemade, highly evolved computer, Euclid. Take a bow, Euc. Thank you. Today our topic is graphing quadratic functions. We'll show you different forms of a quadratic and see how they are represented as a graph.
We'll also talk about such terms as vertex, axis of symmetry, direction of opening, and minimum and maximum values as they apply to graphing a quadratic.
We'll deal with completing the square so that a quadratic can be more easily plotted.
And we'll solve Christine's pricing problem at no extra charge. But let's begin with a short summary of just what a quadratic function is. This is the general form of a quadratic function. Y equals a x squared plus bx plus c. There must always be some value of x squared in the equation. But remember, this is the general form, and not all quadratics look like this when you first meet them.
But however they are written, quadratics all have one thing in common, and that is that when you graph them, they always give a characteristic curve. That curve is called a parabola, and it turns up naturally in a number of places. Euclid, roll clip. The arc of a bouncing ball is a natural parabola. Suspension bridges also form a curve that is a parabola. We use parabolas in receivers and satellite dishes because they have unique focusing characteristics. And sometimes we just use parabolas because they have an eye-catching shape.
The curves you just saw are all parabolas or nearly parabolas, but they have different characteristics. One curve was wider, another was narrower, one opened upward, another opened downward, and so on. Those differences are produced by changes in the quadratic function. For example, let's see what happens if I plot this function. Y equals x squared. Euclid? Here is a basic parabola, but we're only looking at a portion of it. It extends infinitely. Right away, I can see that it is centered on the y-axis. Every parabola has an axis of symmetry, which divides the curve into mirror images. I could fold it in half along this line, and the two halves would match. In the case of this parabola, it is the y-axis which forms the axis of symmetry. The point where the curve crosses the axis of symmetry is called the vertex. But now let's see what happens if I plot a slightly different equation. If I plot y equals 3x squared, I find that the curve, which is still a parabola, is much steeper than when the coefficient is 1. Now, let's see what happens if the coefficient of the x squared term is a fraction. In this case, the curve expands. It doesn't climb as steeply, but it's still a parabola. Let's take a closer look at why this happens. In the three examples we just looked at, the coefficient of the x squared term was different. In the first function, the coefficient was 3. In the second, it was 1. And in the last, it was 1/2. Now, let's look at one specific value, say when x equals 2. In the first function, if x equals 2, then y is 12. In the second function, if x equals 2, then y is 4. Lastly, when the coefficient is 1/2, if x is 2, then y is 2.
In other words, by looking at the coefficient of the x squared term, we can predict if the parabola will be very tight or wide open. Will it shrink or expand? In fact, we can predict a great deal about a graph by inspecting the function being plotted.
Suppose that we have a function y equals -2x squared. A coefficient of 2 means that it should be a tighter curve than the equation y equals x squared. But what effect will a negative coefficient have? Euclid? In this case, the negative coefficient reverses the direction of opening because the y values are opposite of what they were before. So, now I can say that if the coefficient of the x squared term is positive, the curve will open upward, while if it is negative, it will open downward. Now, let's try another variation. What if y equals to x squared plus 2? This time, the vertex is above the x-axis, and it is the same distance above the x-axis as the value added to the x squared term. This is no coincidence. If instead of adding 2, I subtract 3, I find that the vertex is located at 0, -3. And if the direction of opening is reversed because the coefficient of x squared is negative, the vertex is still the same. Let's look at this function. Y equals x squared plus k. Depending on the direction of opening, this value k will indicate the minimum or maximum value of y. If the curve opens upward, it indicates the minimum value of y. If the curve opens downward, it gives the maximum value of y.
So far, all the parabolas Kanwal has plotted have had their axis of symmetry on the y-axis of the graph. But that doesn't always happen. Depending on the equation, a parabola can have its vertex anywhere.
That's right. We've looked at what variations will move the vertex up and down the y-axis. Now, let's see some examples in which the vertex moves along the x-axis. Let's look at this function. Y equals bracket x minus 3 bracket squared. Euclid, plot this one, please. This time, I see that the axis of symmetry has shifted to the right, and it has shifted by 3, the amount subtracted from x in the equation. The axis of symmetry can be found by looking at the squared term and asking what value of x will make that term equal 0. So, if x minus 3 equals 0, then x must equal 3. And that is where we found the axis of symmetry. Let's look at another example. Y equals bracket x plus 4 bracket squared. If instead of subtracting, I add some value to x, can you predict what will happen to the axis of symmetry? If you said it will move in the other direction, you're right. Euclid? If x plus 4 equals 0, then x must equal negative 4. And that is where our axis of symmetry is.
So by just looking at a quadratic function, you can predict a lot. We've shown you how to find the axis of symmetry, how the minimum or maximum values of y are determined, and what indicates the direction of opening.
Let's try inspecting an equation and see if we can predict what a graph of it will look like. My equation is y equals negative 3 x squared plus 3. Let me demonstrate with this plastic curve. Right away, I see that the coefficient of the x squared term is negative, and that tells me that the curve will open downward. Next, I see that the coefficient of the x squared term has an absolute value greater than 1, so the curve will tend to be tighter and steeper. In other words, the parabola shrinks. Because there is a value added to the x squared term, the vertex will move upward, in this case by 3. 1, 2, 3. And it will be a maximum value rather than a minimum. Finally, from the form of the x squared term, we can tell that the axis of symmetry will be the y-axis. Let's get Euclid to plot it with a little more precision. Our prediction has proved correct. Now, let's try one more example. Y equals 1/2 bracket x minus 3 bracket squared plus 4. How will this compare with the parabola for y equals x squared? I see that the coefficient of the square term is positive and less than 1. So it'll open upwards and be wider than this parabola. Next, I see from the square term that the axis of symmetry will be shifted from the y-axis to x equals 3. And finally, because there is a numerical value added to the square term, the minimum value will be greater than 0, and that is the graph for this function. The information we discover in a function can also be shown in table form. This information can be very helpful when predicting the shape and location of the graph of a quadratic function, and will therefore help you to estimate the solutions. Let's compare these two functions by filling in this chart. The axis of symmetry in the first function we know is x equals 3, because x minus 3 must equal 0. In the case of the second function, the square term is x plus 2. If x plus 2 equals 0, what value will x have? X will equal negative 2. Therefore, the axis of symmetry for the second function will be negative 2. Now, let's look at the vertex. We know that the x-coordinate of the vertex will be given by the position of the axis of symmetry. In the first function, that is positive 3. The y-coordinate in the pair is given by any quantity added or subtracted from the squared term. In the first function, that is positive 4. So my vertex is 3, 4. In the second function, the x-coordinate will be negative 2. And is any value added to or subtracted from the squared term? Yes, negative 1. So the y-coordinate is negative 1. My vertex is negative 2, negative 1. Now, let's look at the direction of opening. Remember, this is given by the sign of the coefficient of the squared term. If it is positive, the curve will open upwards. If it is negative, the curve will open downward. Looking at the first function, I see the coefficient is positive, so this opens upwards. And looking at the second function, I see the coefficient is negative, so it'll open downward. Now, in the next part of the table, we compare the curve to a parabola in which the coefficient of the square term is 1. Remember that for this comparison, we're only looking at the absolute value of the coefficient. If the absolute value is greater than 1, the curve will shrink or be tighter. If it is less than 1, in other words, a fraction, the curve will expand. In the case of the first function, the absolute value of the coefficient is 2, so it will shrink. And now looking at the second function, will it shrink or expand? The absolute value is 1/4, which is less than 1, so it will expand. And finally, I look at the minimum or maximum value, which I can find by looking at the direction of opening. If the curve opens upward, the curve will have a minimum value, but no maximum value. That is the case with the first function. Now I look at the second function, it opens downward, so will it have a minimum or a maximum value? If you said a maximum value, you're right. As you can see, we have been able to compile a great deal of information about the graphs of these two functions without plotting.
To get that information, though, you need to have the function in the proper form. This is the standard form of a quadratic function. Y equals a x minus h squared plus k. Now, let's turn this alphabet soup into something a little more visual, plotting. Together, these terms will define the parabola. Let me show you how. Euclid? The absolute value of the coefficient tells me if the curve will shrink or expand. If a is greater than 1, then the parabola shrinks. And if it's less than 1, the parabola expands. The sign of a indicates if the curve opens up or down. Positive a opens upward. Negative opens downward. Okay, let's go back one step, Euclid. The value of h tells me where the axis of symmetry is. If h is -3, then x must be +3. And if h is +3, then x must be -3. Now, for the variable k, the value of k tells me how much the curve moves up or down the y-axis. If k is positive, the curve moves up. And if it's negative, the curve moves down. In other words, it tells me the maximum or minimum value of y, depending on which way the curve opens. Finally, the vertex is given by the values of h and k, h being the x-coordinate and k being the y-coordinate. And here's a special note. You'll notice that the value h in this function is +3, but the standard form of the quadratic function is x minus h, so this changes its value, thus giving us the coordinates -3, -5.
So you can see that the standard form of a quadratic equation is very useful. But what if you come across a quadratic which is not in this form, like this one? Y equals 3x squared minus 12x plus 1. This form can be converted to the standard form through a process called completing the square. Watch. The first step is to factor the terms with the x in them, so that the x squared term has a coefficient of 1. Now, 3 is a common factor in both 3x squared and 12x. When I factor this, I get y equals 3 brackets x squared minus 4x brackets, and then I bring down the plus 1. So now the x squared term has a coefficient of 1. Before I go any further, let me explain what I'm about to do. I want to convert this function into the standard form. Notice the standard form has the contents of the brackets all squared. However, in the example, the square is embedded in the brackets. To convert this, I'm going to complete the square. Now here's how it works. I'm going to change this into a trinomial that when factored will give me this format. So let me make some room. Y is equal to 3 x squared minus 4x plus some room here plus 1. By completing this trinomial, I'll be creating an expression that is a perfect square. Thus the name, completing the square. So now the question is, what trinomial will give me a perfect square? Well, there's a little trick to it. First, look at the coefficient of the x term. Divide this coefficient by 2. In this case, it's -4. Divide -4 by 2. That gives me -2. Then square it. -2 times -2 is +4. So I complete the square by placing a +4 here. The trinomial will factor into a root of this form, x minus h squared. We'll factor that in a second. Before I go on though, always remember that you have to keep equations in balance. If I add something here, I have to subtract it elsewhere. I'll do that at the end here. If I simply subtract 4, that won't be sufficient because +4 is also multiplied by 3. So 3 times 4 is 12, so I must subtract 12. This gives me y equals 3 brackets x squared minus 4x plus 4, combine the terms, minus 11. Now, I can factor the trinomial. The trinomial, when factored, equals x minus 2 all squared. Writing in standard form, this gives me y is equal to 3 x minus 2 all squared minus 11. The conversion is done. It's now in the standard form and can be easily graphed.
Okay. Oh, the deadline's today. Okay. I'll have to call you back, okay? All right then, bye-bye. Kanwal, that was the editor of the Math News. She needs the ad copy today. The deadline is today. Okay, now I have it all ready, but I don't know what price to put in. Are you ready to solve this pricing problem for me or
Yes,
what?
Christine, that's her next item of business. But first, we need all the information on this.
Oh, okay. I made this chart. Look at this. Isn't this beautiful?
Oh, that's nice.
Okay, so when I was selling the magnets for $24 with no price reduction, I had no customers.
Right.
Don't start. When I lowered the price $1 and sold them for $23, I got 10 customers.
Right.
And when I lowered it another $1 and sold them for $22, I got 20 customers. So it looks to me like there's a pattern here that every time I lower the price $1, I get 10 more customers.
Yeah, the pattern's pretty clear. You know, as your price reduction was 0, your revenue was again price times the number of customers, or 24 times 0, which is 0.
Right.
And when you reduce by 1, you had price times the number of customers, or 23 times 10, which is 230. And here, our revenue is 22 times 20, which is 440. And from this, I know if your price reduction was, let's say, x, your price will be 24 minus x, and the number of customers will be 10x. And again, to get the revenue, I go price times the number of customers, or 10x times 24 minus x.
Yeah, but that still doesn't tell me what my maximum profit will be.
Well, not directly. But you see, if we multiply 10x by 24 minus x, I multiply x times x, which gives me an x squared term. And that is a quadratic function. And we can find the maximum value by graphing it.
Ah.
So, let's work out this function first. Let's call our revenue y. So y equals 10x times 24 minus x. We multiply it through and we get y equals 240x minus 10x squared. We put these in descending order of powers and get y equals negative 10x squared plus 240x. And now we want to complete the square to get into standard form. So first I factor the x squared term to give me a coefficient of 1. Y equals, I factor out a negative 10, brackets x squared minus 24x. And now I ask, what can I add within the bracket to make a perfect square? Remember the trick? Take the coefficient of the x term, in this case negative 24, divide by 2, which gives me negative 12, and then square it, which gives me 144. So let's do that. Y is equal to negative 10, bracket x squared minus 24x plus 144. And to maintain my equation, whatever I add within the bracket, I have to compensate for it outside the bracket. And remember that what is within the bracket is multiplied by negative 10. So I must add the opposite of negative 10 times 144, which is negative 1,440. So I must add 1,440 here. Now I find the root of the perfect square, which is x minus 12 squared. And I have the equation y is equal to negative 10 brackets x minus 12 squared plus 1,440. And my equation is in standard form, ready for plotting. So take it away, Euclid. Euclid has used different scales on the x and y axes, and he has labeled the axes. The y-axis is revenue, and the x-axis is price reduction. When we plot the function, here's the parabola we get. You can see that when the price reduction gets to $24, your revenue drops to 0. That's because the price reduction will then equal the original price, and you'll be giving your product away for free. But the revenue y reaches its maximum of 1,440 at the axis of symmetry of the curve, which is found at 12. So, Christine, that means
What? We're out of time?
No, it means that if you reduce your price by $12, you will make the most money.
Oh.
And now we're out of time.
Oh.
Yeah.
Oh, 12 bucks. Well, that's good. Well, goodbye and thanks for watching. Tune in again next time to Math Shop, where we make mathematics profitable.
Goodbye.
12 bucks.
I think you should phone Frank about that.
Who?
Frank, your cousin?
Oh, Frank. Frank. Yeah. Right. Thanks, Kanwal. Oh, this will be good news. Okay.
You know, I think even 12 bucks is too much for these ones.
Well, they're not magnetized.
Oh.
That's why they're 12 bucks. You just tape them on the fridge.
Oh.
Hi, Frank. 12 bucks. Yeah. Well, no, I think it's a great price.